Good afternoon, Professor.
Hello guys, nice to see you. How was your weekend?
Good, actually. And yours?
Yeah, not bad. Yeah, hi guys. Hello everyone. Okay. So I received a bunch of complaints on some problem during the homework assignment, week 13. Regards one of the problems that it doesn't accept appropriate format of answer. So we will take this into account, double check, and make some changes if necessary. Okay, so I believe we can continue with our discussions, and today we will discuss heat engines and second law of thermodynamics, which is very closely related to this to heat engines. So let me change the camera. And so let us give first definition. What is sorry? What is a heat engine? And this is some device, some system that takes in energy by heat and operating in a cyclic process expels a fraction of that energy by means of mechanical work. So it actually transformer of energy accepted by heat to some mechanical work. And in general, it can be represented with this simple schematics. So we have some high temperature body or reservoir which doesn't, the temperature of this reservoir doesn't change over time, so it's constant. So it will be a high temperature reservoir or body, doesn't matter. Then we have our heat engine. We provide some energy in form of heat to this heat engine. That will be Q high, H. Then this heat engine performs some work on external environment. Some work is done, and then residual heat, residual energy is transferred by heat to the cold body or cold reservoir. So this heat will be denoted as QC, Q cold. So there are, as I already described here, like 3 steps in talking very generally about the principle of work of heat engine. We provide some energy from high temperature body to the heat engine by heat. Then heat engine performs work and expels the rest of the energy by heat to the cold body. So work which is done by such heat engine is equal to the difference between received energy by heat from high temperature body and expelled by heat to the cold body. So since the engine, the heat engine, works in a cyclic process, and that means that the working substance is some working material which is utilized in heat engine. Can be different, but in general we call it some working substance. It undergoes also cyclic processes. That means if we consider, so it comes back to initial set of state parameters, and that means that change in internal energy, like difference between initial and final point of this cycle, since it comes back to the same condition, is equal to 0. So we don't have any changes in internal energy over one cycle. And obviously, if it's some device which converts one form of energy to another form, it should be described with a certain parameter which determines efficiency of such device. So efficiency of a heat engine can be calculated as a ratio between mechanical work done by this heat engine and energy which is received by heat from the high temperature body. So taking into account the difference that work is done is difference between QH and QC, then we can write QH minus QC divided by QH, or it is unity minus QC divided by QH. So this is the definition of efficiency of such heat engine, and we see that it will be equal to unity. Well, first of all, efficiency is equal to 0 if there is no temperature difference between hot and cold bodies, and this nominator here, QH minus QC, is equal to 0. So obviously, if there is no difference in temperature, this heat engine will not operate. However, there are other extreme case when we, what we're kind of more interested, when E is equal to unity, or we can write like 100%, so we can multiply here by 100%. It doesn't change anything. So this case is possible from this form of writing the this equation for determining efficiency only when QC is equal to 0. So this is impossible, since all real heat engines, they work with much lower efficiency than 100%. And this brings us to the definition of the first, the second law of thermodynamics from the point of view of heat engines. So we will give a bit other formulation later, but from point of view of heat engine, it's so-called Kelvin-Planck form of the second law of thermodynamics. It tells that it is impossible to realize a heat engine operating in a cycle which converts all input energy into work. So it's impossible to make such a heat engine when work will be equal to all input energy via heat transfer from a high temperature body. So this is impossible, and this is actually the second law of thermodynamics, one of formulations of this law. So at the same time, we need to highlight here that for all heat engines, energy is transferred from hot body to cold body. So we have some energy transfer via heat through heat engine, which performs some work, but the flow of energy is quite natural. That's what we experience under normal everyday conditions. However, it is possible to reverse this system and use heat engine as a heat pump or refrigerator. So in this case, we have very similar picture, but it's actually working in opposite direction. It will be high temperature reservoir, then heat pump, then we have a cold reservoir, and we get some energy transfer from the low temperature reservoir, QC, to heat pump. We perform some work on the system from environment, and that makes this heat pump to transfer further energy via heat, U high, to high temperature body. So it works exactly in the opposite direction. And it is in order to realize such a natural flow of energy from cold body to hot body, we need to perform some additional mechanical work on this system. And we will discuss this on some clear example, like working principle of refrigerator. I believe it will be useful to discuss this in details, so you have very clear understanding how a refrigerator works, but a little bit later. So first we we need to define so-called coefficient of performance. So that is the we have some efficiency to define efficiency of heat engine. In case of heat pump, we operate with so-called coefficient of performance. It is COP, and it could be considered for cooling and for heating. So depends how it works. So for example, refrigerator works its main job to cool down some closed volume. Then we consider COP for cooling, and that is QC divided by work. So this is the ratio between the energy which we took out from the system, like cold system, by heat, to the amount of work which had to be done to realize this. And there is another, so this will be for cooling. Let's put here C. And COP for heating is equal to QH divided by work. So that defines the performance of heat pump in terms of how much heat we transferred to hot, how much energy we transferred to hot body by heat as a ratio to necessary work to realize this process. So both are important because these machines, like devices, are generally used for both purposes. As I mentioned, refrigerator, we need to cool down some volume, and then we care about cooling. However, heat pumps also quite widely applied in heating like houses or apartments, homes, and in that case, it works between two environments. One is external air, like in environmental air at low temperature usually, and then air inside the house, which is at 25 degrees Celsius. So in this case, we want to transfer heat from outside, from cold air to inside, to hot air. And that is possible by performing some work. So we utilize some compressors in these systems. And for instance, for many commercially available heat pumps for heating apartments or houses, this COP for heating is in the range of 4 at temperature outside about -4 to -5 degrees Celsius. So if temperature drops outside, then of course the COP also drops. And that's why it's not commonly used in areas where temperature outside drops to low values like -15, 20, and less degrees of Celsius. However, in moderate climate where temperature of -5 degrees Celsius is considered to be one of the lowest values, it's quite efficient because this number 4 COP equals about 4 means that we spend 1 kilowatt of electrical energy to perform work on this heat pump, and instead we get 4 kilowatts of power in terms of energy transfer by heat to our internal environment. And that is huge gain, because otherwise if we just use some electrical heater, we would get exactly this 1 kilowatt power and nothing else. So this heat pump can be very efficient in under certain conditions for warming up our homes and apartments. However, it's not so commonly used as air conditioners, so it works in the opposite direction, but it's getting more and more popular nowadays. So now I think that it is reasonable for us to discuss in details how refrigerator works and how it realized in main points, structural units of refrigerators, which we have everywhere nowadays, like based on such working substance as Freon. So here we will not consider Peltier elements, which are semiconductor thermoelectric coolers. That's another option to cool or heat up some environment, but that is involving physics of semiconductors. However, thermodynamics also works there, the same way. It's just different devices, and we will not discuss them now. So now it's a classical refrigerator. So with working substance Freon. So I will not specify what kind of boiling temperatures at which pressures Freon possess, because there are different types of Freons and they are used for different refrigerators. However, we need to understand that Freon is such a working substance which has very low boiling temperature at low pressure. So you know that boiling temperature depends on pressure. So if we reduce pressure, water, for instance, will start to boil at lower temperatures than 100 degrees Celsius. So Freon has like more extreme dependence on pressure in terms of boiling temperature, and some sorts of Freons, they are at low temp or at low pressure, they can start boiling at temperatures which are like minus 20 degrees Celsius. So this is a very important feature of Freons, that they can boil at such low temperatures. And then if we increase pressure, this boiling temperature will significantly increase also. So based on this feature, the difference of boiling temperatures of Freon at different pressure, we design all these types of refrigerators. So now let us consider more in details how it's technically realized. So every refrigerator consists of two main blocks. Let's show it like this. So one is evaporator. Another is condenser. So evaporator is actually our freezer chamber in a refrigerator. So we have some pipes which are going through the walls of freezer. And here we have low pressure, and low boiling temperature in this area of evaporator. Since we have low pressure and low boiling temperature, what happens? Freon from liquid condition, it evaporates very actively because temperature of some products which we put in the freezer is higher than temperature of boiling temperature of Freon. It evaporates, and evaporation is a phase transition when Freon absorbs energy like by heat from the environment of this freezer and converts it to the phase transition. So it becomes goes from liquid to gaseous phase transition. So it means that we, by providing to this evaporator liquid Freon at low pressure, we will get conditions when even cold environment will still provide some energy by heat to this freon, since it starts to evaporate at very low temperature, about minus 20 degrees Celsius. So that is why usually commercially available freezers, like refrigerators with freezers, they work at a temperature of minus 18 degrees Celsius. So then once this evaporation happens, like boiling of freon, it goes not so early, maybe need some space there. Let's put it here. It goes down from our freezer, and usually if you look from the back side of the refrigerator, there is on the bottom there is such black volume which is connected to some electric actuator like motor, and that is a compressor. So we have compressor which works like this in this direction. So what compressor does? I mentioned that here we had low pressure, low boiling temperature. Freon evaporates, and in this area we have freon vapor, but still it is low pressure area. Now we need to perform some work on the system because it's heat pump, so we need some external work to be done in order to make it work. And this work is done in refrigerators by a compressor. So what it does, it increases pressure of this freon vapor. It's only one work to be done by this compressor. So here, after compressor, we have much higher pressure of freon vapor. And of course, since this compressor performs some work on the system, we increase temperature. So here we already have high temperature, which is about 50 degrees Celsius. So this is temperature which even for high pressure and also high temperature and high pressure. So we will write it here. Also high temperature, high pressure. High temperature and high pressure. Our boiling temperature is now much higher, but still it is not higher than 50 degrees Celsius. So it is something like 20 degrees Celsius, 20, 25 degrees, like 30 degrees Celsius. So we still have gaseous phase of freon at 50 degrees Celsius at high pressure. Then this high pressure vapor at 50 degrees Celsius goes to the condenser. Condenser is such a grid, you may notice it, such metal grid behind your refrigerators, which gets, it stays always warmish. So it's not hot, but it definitely warmer than environment in your kitchen. So that is because this 50 degrees Celsius heated high pressure vapor of freon goes to this metal grid to cool down. It goes through all this long metal pipe behind the refrigerator. and cools down to room temperature, like something 25 degrees Celsius. So during this cooling down, since it's at high pressure, boiling temperature is much higher now of Freon, it condenses. So room temperature is low enough to condense this high pressure Freon vapor. And it transforms to liquid Freon while it goes through this condenser. That's why, by the way, refrigerators have automatics, like they stop working at temperatures of environment lower than 15, 14 degrees Celsius. You cannot make a refrigerator work in some cold environment where room temperature is, like, for instance, 5 degrees Celsius. It just doesn't, there is some automatics which even switch off the compressor and it stops working. So you need special design for such refrigerators. Then this condensed Freon, a liquid, needs to somehow be fed in the evaporator. But that should be done very slowly, because if we dump a lot of liquid Freon in evaporator, it will evaporate very fast. That will create some excessive pressure in this low pressure region, and will increase boiling temperature of Freon. So that is not acceptable. We need to keep boiling temperature low. And in order to do that, there is like some pressure regulator, but that could be some capillary, like very thin pipe. Very thin pipe, which provides very limited amount of liquid Freon to be injected in the evaporator. So then from evaporator, we have some pipe which comes here. And since this capillary, let's call it C, is very diameter of the cross section is very small, only very limited amount of liquid Freon comes to evaporator. It evaporates. Again, we have phase transition. We absorb some heat, some energy by heat from cold environment, and this process is repeated again and again. So it just cyclic process, and this is the way how technically is realized heat pump, in particular in refrigerating mode, which we use in our kitchen nowadays everywhere, and also beyond. So this is the working principle, and I believe that could be useful for you guys to have a clear understanding how it works and what is going on there. So as I mentioned, we need to do some work on the system in order to transfer energy from low temperature environment to high temperature environment. And this work is done by compressor in this case. So this is actually the definition, the statement of second law of thermodynamics from the point of view of heat pumps. It is impossible to transfer energy by heat from low temperature environment to heat temperature environment if we don't perform on the system some work from the side of external environment. So if we don't do some work on the system, we cannot transfer energy from high temperature environment to low temperature environment. So this is actually the same second law of thermodynamics formulated from the point of view of heat pumps. So initially we had this definition from the point of view of heat engines. Okay, so I think with this we are done, and now we can proceed further with so-called Carnot engine. So before we start with Carnot engine, I would like to give a definition of reversible processes and irreversible processes. So reversible process of the system which is undergoing some process, thermodynamic process. So this system can be returned to its initial initial conditions, initial set of state parameters, and along the same path on the pressure volume diagram, and every point on this pressure voltage diagram, which describes the thermodynamic process, corresponds to an equilibrium condition, equilibrium state condition. So processes that do not satisfy these requirements, they are considered to be irreversible. And not surprising that all nature processes, like natural processes, are irreversible. It's really not so easy to realize truly reversible process. However, in some approximations, when processes are carried out in very, very slowly, that we can consider at each point state close to equilibrium one, that could come close to reversible condition of reversible process. However, still we have some dissipation of energy because of friction and some other losses, and realize truly reversible process is not possible. However, it is important to understand this concept when we start discussing Carnot engine, because this engine is a theoretical engine device with maximum efficiency, which is possible for a heat engine. And all engines, like heat engines, which can be fabricated, they have smaller efficiency than Carnot engine, because Carnot engine this Carnot cycle goes through a fully reversible cycle, like fully reversible thermodynamic processes, and all other engines by definition have some dissipation of energy that they cannot perform so efficiently as Carnot engine. So there is some first Carnot theorem, and this states that the efficiency of Carnot engine does not depend on working substance, and is defined only by temperature of difference between a high temperature environment and low temperature environment. So this theorem we will prove a bit later when we derive equation for the efficiency of Carnot engine. However, there is another second Carnot theorem which states that actually what I mentioned before, it is Carnot engine's efficiency is the highest than all heat engines, like all possible heat engines which we can make, their performance will be lower. And in order to prove this second theorem, we should perform some imaginary experiment, and we can do this right now. So we have some hot reservoir, then we have cold reservoir, we have Carnot engine, and some heat engine, some other type of heat engine. So let us assume that efficiency of this heat engine, efficiency of heat engine is larger than efficiency of Carnot engine. So in this case, what we can do, since Carnot engine is based on the fully reversible cycle, we can operate it with the same efficiency as a heat pump. So we can operate for cooling cold reservoir and providing some energy by heat to hot reservoir. So of course we need to perform some work on this heat pump based on Carnot engine. And let us assume that our second heat engine will be the device which provides this work. So in this case, it will take energy from high temperature reservoir and provide energy by heat to low temperature reservoir. Since efficiency is higher, we assume that efficiency of heat engine is higher than efficiency of Carnot engine, then we can provide all work which is done by heat engine to Carnot engine, and this work will be more than necessary for going to net zero heat transfer with Carnot engine, because its efficiency is higher. So it means that if we dump expel all work done by heat engine to Carnot engine, it will continuously take some energy from cold reservoir and transfer it to high temperature reservoir. From the point of view of environment, such system is closed, and the net work done from the environment of the system is equal to zero, because besides this heat engine, which is working in contact with the same high temperature and low temperature reservoirs, we don't have any machine which produces work on Carnot engine, and in that case it will be against the definition of second law of thermodynamics, because we have a statement that continuously we can transfer energy from cold reservoir to hot reservoir only when from the side of environment, from outside, some work is done on the system. And in this case, net work is from outside of environment is equal to zero. That's why we cannot design a heat engine with efficiency higher than efficiency of a Carnot engine. So now we will consider step by step the working cycle of Carnot engine, which consists of two isothermal and two adiabatic processes. So we have four processes which form the Carnot cycle. And of course, we need to go through each of these processes. Then we will consider work done by during each of these processes and calculate the performance, like efficiency, derive an equation of the efficiency of Carnot engine. And there we will show that it indeed does not depend on working substance, and that will be defined only by difference in temperature of hot and cold environment. So I think that we are already running out of time, and it would be good to have it in one bulk, this explanation of each process and then calculation of like derivation of the efficiency, because it all connected to each other. In order not to interrupt, I believe that at this point we stop our discussion today. We'll continue on Wednesday. We will finish this discussion on Wednesday on Carnot engine and proceed with with the definition of entropy, and that will be our last topic to be discussed during this course. So on Friday, we will have our last discussion. Okay, guys, thank you very much for attention. Do you have any questions now?
Excuse me, Professor. Can I ask one question about
Yes,
the
sure.
laws of thermodynamics? Actually, when we said that second law states that work cannot be equal to heat, don't we contradict ourselves with the first law?
So you mean
Like in
first law states that change in internal energy will be equal to work plus heat.
Yeah, and at the beginning we mentioned like cycle system when internal energy change is equal to 0, and then the heat will be equal to minus work.
Yeah, but so the thing is that we have always the some heat to expel to the so in theory, in just based on the equation, we can get performance unity like 100%, and that requires this heat transferred from heat engine, which is Q cold, to be equal, like energy transfer by heat to cold environment equal to 0. So in empirical way, any of engine doesn't have even close to 100% performance, and that is shown very well with Carnot engine, because its performance, which is the highest possible, which still cannot be reached, and that already much lower than 100%, would be like 30%, depends on the temperature of cold and temperature of cold and hot environment. And that's why we just cannot realize such process when this heat, which we return to the cold system, will be equal to 0. So based on Carnot and cycle performance, we cannot make a system which will work with higher performance that is fully reversible cycle. And even so, performance is much, much lower than 100%. So that's a definition of first law of thermodynamics, that we cannot convert all heat provided to the cyclic process, because it's not just one process. We can convert all provided energy by heat to work in one process, and that will be like either thermal process. We don't perform any work, but that is just one process. And if we need cyclic process to come back to initial set of parameters, we cannot realize such, because we cannot just come back to by the same path to initial set of parameters. We need to perform like 4 passes. And on the difference between work and heat provided and work done on each of these passes, the useful work will be defined, that we will talk about this a bit later, will be defined by the area which enclosed in this cycle of heat engine. So eventually we will get conditions when we lose energy in any way.
Okay, thank you very much.
It's like works against itself in order to come back to initial set of parameters. And you need to subtract this work done by successive processes which come, like push the system back to initial set of parameters. So on the difference between this work, we have losses, and eventually doesn't work that we can convert all heat to work.
Okay, thank you.
Yes, thank you for your question. Okay, guys. Thank you very much for your attention, and see you next time on Wednesday. Bye-bye.
Thank you very much. Have a nice day. Goodbye.